In this video, we will quickly look at several integrals and just discuss the initial strategy to get started. In this example, I have the integral of e to the square root t divided by the square root of t dt. Here I would do a substitution. I would let u be the square root of t. The big clue to do this is how I have the square root of t inside the exponential function. In this problem, I have 12 to the y power minus 3 to the y power divided by 6 to the y power dy. Here, I would use algebra to rewrite the integral, splitting it up as fractions. 12 to the y over 6 to the y minus 3 to the y over 6 to the y. And then each of these fractions I can simplify. So we have 2 to the y power minus 1/2 to the y power dy. Then we can just integrate directly. Here are three integrals that initially look similar but actually have different strategies. In the first one, we have x squared divided by the square root of x squared plus 9 dx. In this one, I would use trig substitution. The reason is that I see the square root of x squared plus 9 on the bottom of this fraction, and a direct u substitution will not work. For my trig substitution, I would let x be 3 secant of theta. In the next integral, we have the antiderivative with respect to x of x divided by the square root of x squared plus 9. Here I would do a direct substitution, choosing u to be x squared plus 9, so 1/2 du will equal x dx, and my integral becomes the integral of du divided by the square root of u with a constant of 1/2 in front. I can finish this by rewriting the square root of u as a power and using the power rule for antiderivatives. For this integral, we have x squared divided by the square root of x plus 9 dx. Here, I would do a substitution. I would choose u to be the square root of x plus 9. Then 2 du equals 1 over the square root of x plus 9 dx. So the 2 du will take the place of the square root on the bottom along with the dx. For the x squared on top, I will solve this equation for x. So if u equals the square root of x plus 9, then x equals u squared minus 9. And we can rewrite the integral as the integral of u squared minus 9 squared times 2 du. From here we can FOIL this out and use the power rule for antiderivatives on each term. Here's our next example. We have the integral of tangent to the third of theta times secant of theta d theta. Here we see trig functions, so we are thinking back to the strategies we know for integrating with trigonometric functions. We know with tangents and secants, we either want to keep a secant squared, which we cannot for this problem, or we want to keep a secant tangent. So I would rewrite this as tangent squared theta times secant theta tangent theta d theta. Then I would use our trig identity to rewrite tangent squared theta as secant squared theta minus 1. And now we can do a substitution where u equals secant of theta, and the du will take care of the secant theta, tangent theta, d theta that we have here at the end. Here we have the integral of dx divided by x to the 4 minus 16. Because this is a rational function, the best strategy to choose is partial fractions. So I would start by writing 1 over x to the 4th minus 16, which is our integrand, and factoring the bottom, which would be x squared plus 4 times x plus 2 times x minus 2. Then we would get the partial fraction decomposition. From here, I would clear fractions, solve for the constants, and split my integral up by term. Here we have the arcsine of y dy. So I certainly do not know the antiderivative for arcsine of y. In fact, I don't know much of anything I can do with arcsine of y. However, I can take the derivative of arcsine y. So wouldn't it be nice if there was a way I could take the derivative as opposed to the antiderivative? Luckily, there is. That's integration by parts. So I'm going to do integration by parts. I'm going to choose u to be arcsine of y and dv to be dy. Then my du is 1 over the square root of 1 minus y squared dy, and v equals y. And then our integral is y arcsine of y minus the integral of y divided by the square root of 1 minus y squared dy. Now we do still have an antiderivative to deal with, but here we can get away with u substitution. Choose u equals 1 minus y squared.